Hello everyone, welcome to my YouTube channel. So today I am going to discuss an interesting problem from CSIR NET 2023 December exam. So this question is from field extension and this is a nice problem. So I'm going to solve it. The question says that consider the field of complex number with Euclidean topology and let K be a proper subfield of C not contained in R. That means K contains at least one uh, complex number, I mean non-trivial complex number. Then which one of the following is correct? So option 1 is K is dense in C, option 2 is K is an algebraic extension of Q, option C is algebraic extension of K, and option D is smallest closed subset of C containing K is not a field. So we know that it's a basic thing that we know that Q is already contained in K, right? Because Q is the prime subfield of so Q is already contained in K. You can just easily show it by uh, seeing that 1 is in K. That means any natural number is in K. That will imply any integer is in K, and since this is field, so 1 by n types all of these are in K, so m by n also belongs to K, and that will imply that Q is already contained in K, right? Okay, now, so is it always true that K is an algebraic extension of Q? This is not necessarily true. Why this is not necessarily true? So say you can take K to be Q I comma pi. Okay, Q adjoint I comma pi. Then clearly it is not contained in R since I is in K, right? Okay, and clearly K is not equal to C. K is proper. This will imply K is proper, right? And K is not an algebraic extension. It's not an algebraic extension of Q. Why? Because pi is not algebraic over Q, right? Pi is a transcendental number, so that's why the second option is wrong. Now it is saying that C is algebraic extension of K, right? This is also not true, because if C is, this one is K, C is algebraic over K, and if you particularly choose K over Q such that K is algebraic over Q, then this will imply that C over Q is algebraic extension, which is a contradiction, right? So in particular you can take K to be, say, Q adjoint I, right? That means C is not algebraic extension over K, because in particular you can take pi is in C, but pi is not algebraic over Q adjoint I. So that's why C is also wrong, right? Now I'm going to show that K is dense in C. It is very interesting result that K is dense in C, and proof is very simple. So how can I prove that? So C, and this is Euclidean topology, right? Okay, and K is contained in, say, C. This is a subfield which is proper subfield, right? Proper subfield. Now I am denoting K bar as topological closure. Okay, I mentioned already this, that this is topological closure, not algebraic closure. Okay, mind it. So K closure, I am denoting it as topological closure, and so my first claim, K closure, that is topological closure, is a subfield. Why? Because that is easy to it is easy to check. Why? It is easy to check. Let X belongs to K closure. Let's give it name L. Y belongs to L. So since X belongs to L, that means there exists a sequence Xn that converges to X such that Xn contained in K, and Y belongs to L implies there exists sequence Yn converges to Y where Yn belongs to K. Now K is a field, that means Xn plus Yn, which is equal to say Zn, this is already contained in K, and then Zn converges to X plus Y. That will imply X plus Y is in K closure, which is L. It means X plus Y is in L. Similarly, multiplication also holds, right? Why? Because if Xn converges to X and Yn converges to Y, then Xn times Yn converges to Xy. And similarly, if Xn converges to X and X is a non-zero element, that means 1 by Xn also converges to 1 by X. That is basic results of limit. Hence, L is a subfield of C. Right? Now Q is contained in K. So topological closure of Q is R. So R is already contained in L. Because Q is contained in K, that will imply that Q closure, I am talking about topological closure here, okay, that is contained in K closure, which is L. So, and topological closure of Q is R. So R is contained in L, right? So that means we have R is contained in L, that is contained in C, right? And we know that the extension degree of C over R is 2, and L is a subfield contained in C, and 2 is a prime number. That will imply that extension degree of C over L is 1, which implies that C equal to L. That means topological closure of K in C is C. That will imply K is dense in C. Right? So hence option A is correct. And it is saying that smallest closed subset of C containing K is not a field. So smallest closed subset containing K means topological closure of K, and topological closure of K is C. That means it is a field. Hence D is also wrong. So option A is correct. Okay. I hope it is clear to all of you. Thank you.